So here we have question 3 from online activity 2. We've got a piston cylinder device. Initially contains air, so ideal gas, at 100 kilopascals, 10 degrees C, and the volume's 2 meters cubed. We're going to heat it up until the temperature reaches 250 degrees. We want to know the amount and heat input into the air in kilojoules and the final volume. So this is very similar to the first question in this set. Difference is we have a piston cylinder device. So here's our system. Time 1, we have 100 kilopascals, 10 degrees C, and volume at time 1 is 2 meters cubed. We're going to heat it up until time 2 reaches 250 degrees C. Since it's a freely moving piston cylinder device, I know that P2 is P1 is 100 kilopascals. So I have all the information I need at time 1 and time 2. So first thing is how much heat was put into the air. So our general conservation of energy equation, heat in minus heat out, plus work in minus work out, minus the boundary work, equals the change of energy of the system. There's no heat loss, it's not doing any work, no work's being done on the system. There's Q in, right? That's all we have. There is boundary work though, because this system is going to change size, right? This piston's probably going to move up, the volume's going to get bigger. There's work associated with that. So we need that, equals the change of energy of the system. Boundary work is integral of PdV. In this case, pressure is a constant, so we have pressure times V2 minus V1. And I can use the definition of specific volume to say that this pressure times mass, specific volume 2 minus specific volume 1. So I factored out the mass because mass 2 and mass 1 are the same. So now I'll put this in here, add it to the other side, and then group everything with 2 and everything with 1. So Qn equals mass times, and so I'll have a mass times a U2 that's positive. And when I take this to the other side, add the boundary work, so I have a positive that on the other side. I have P times V2, so I factor that mass out. Alright, and the negative terms are U1, and another negative term is pressure times V1. Pressure 1 and 2 is the same, right? So I can put a 2 there, a 1 there. And this, by definition, is, this is H2. Enthalpy is defined as U plus PV. So Qn, I'm going to put it over here. Qn is mass times H2 minus H1. So all I need is enthalpy 1 and enthalpy 2. I could take this one step further if I wanted, and I could use Cp, so I need the mass first. Mass times Cp. Cp, because this is a change in enthalpy, times T2 minus T1. We're not going to do this though because we have table A17 and we can directly look up the enthalpies. So here's what we've got. The initial mass, this is the same exact initial conditions that we had earlier, right? So we can use ideal gas to find that the mass was, what did we have earlier, 2 point something? Let's find it. Looks like 2.46. Times, oh, we did it wrong earlier. Okay, 2.46 times. Now we need the enthalpy at 250 degrees C. which is 523 Kelvin, so that's about 526.7 or so. Minus, initial condition was 10 degrees C, 283 Kelvin. So we go to table A17 and find the enthalpy at 283 Kelvin is pretty much 283.1 kilojoules per kilogram. So we can calculate Qin. Looks like 599.8. Kilograms go away, we're left with kilojoules. Okay, we got the amount of heat input. The other thing we were interested in is what's volume 2? Should have written that initially. So we have, we get a little bit of space, maybe in the middle here. So we have closed system, ideal gas. P1 V1 over T1 equals P2 V2 over T2. I know that pressure 1 and 2 is the same. I'm interested in V2. So V2 is V1 times T2 over T1. So we started with 2 meters cubed times T2 was 523. T1 was 283. And so volume 2 is 3.7. So the volume almost doubled, not quite.